you. Thank you, Christina. Thank you for the invitation. So I will show you a quantitative definition of the increase of the detection efficiency that we can obtain for Coca-Cola supernovae when we join together neutrino and gravitational wave detector. So I will, of course, show you what are the assumptions that I am going to do in the neutrino sector, in the gravitational wave sector, what are the emission model that I'm going to use, and what is the analysis that I'm going to do. And I will show you the data analysis that you can obtain improved in the neutrino sector by using some more defined shape parameter. And then finally, I will show the results of the multi-messenger analysis, taking into account both gravitational wave and neutrino. So let's start with the network of detector that I'm going to consider. So I'm going to consider the 3 interferometer, LIGO and Virgo working together as usual, and 3 neutrino detector, LVD, that is 1 kiloton scintillator in the Gran Sasso laboratory, Camland, and Super K. And for the gravitational wave sector, I am going to use the standard pipeline that is used inside the gravitational wave detector to look for a modeled burst of gravitational wave that is coherent wave burst analysis. And from this analysis of the gravitational wave side of this network, you will find up with a list of gravitational wave triggers. Then I will proceed with the neutrino side analysis, and also in this case you can combine different detectors in order to have at the end a list of neutrino trigger in coincidence inside the network. And then you look for temporal coincidences among the 2 messengers by assuming a temporal window. So let's see the assumption in this case. So every time that you work in a network of different detector, or also in a network of detector in general, you have to assume a priori what is the threshold in terms of false alarm rate that you want to obtain in order to be safe. So in our case, we set a threshold that is 1/1000 years, and we also require at least 2 neutrino in coincidence with the gravitational wave trigger. And then we decide what is the temporal window that we want to use in order to look for coincidences. We set this window to 10 seconds in order to accommodate the majority of the models. And then we require for the neutrino sector, so only for the network of neutrino detector, the threshold in terms of false alarm rate 1/100 years. This threshold is the one that is used actually in the S-News. So in order to be safe, we decided to use the same threshold. So let's see now the assumption in terms of emission model. So let's start with the neutrino. So we decided to use an emission model from numerical simulation, that is this one from Eodolf PhD thesis of 2014, and one that is data-driven, if you want, from Supernova 9087A. So we use also a phenomenological description of the emission that is described by a temporal function like this one with 2 different time scale, so the rising time scale and the decay time scale. And these 2 time scale are fitted on Supernova 9087A data, and we found out this best fit for this value. So the rising time is 0.1 second, and the decay time is 1 second. And then these are the average energy that we obtain by the fit of Supernova 9087A data from the different flavor, assuming normal mass hierarchy, and this is the total binding energy. So we use both in order to cover, if you want, the uncertainty that we have also in the neutrino sector in terms of emission model. Of course, you can use other model, but I will show you that this is not really important in this discussion because neutrino detectors are very efficient. So let's go on. So with this assumption, let's see what is the expectation in the 3 detectors that I considered, so the large volume detector, Camland, and Super K. So these are the number of events that you can obtain, inverse beta decay events, for the different detector for a supernova 10 kiloparsec away by assuming this energy threshold in this analysis. And then we also simulate, of course, background for all these detectors. So we simulated 10 years of background. Then in this background, we inject signals for different distances for different model, 100 of signal for each distance and for each model. And then we define what is the analysis efficiency in terms of number of recovered signal over the total injected signal for each distances. And this is the one that I will show you now, so the efficiency in this term. So there is not any requirement in terms of statistical significance. There is just the requirement to see the signal. And this is important for relevant for further discussion that we are going to do. So let's see the efficiency. So these are the efficiency, the detection efficiency for the different model and for the different detector that we obtained. And as you can see very well, the Milky Way will be covered by all these detectors with 100% of efficiency. The Large Magellanic Cloud, still Super K will have 100% of efficiency, while for the LWD and Camlan detector that are smaller, we start to have a decrease of the efficiency that could be also dependent on the model, in this case, of the mission model that we considered. For Andromeda, the efficiency go to 0 for all the detectors. So now let's move to the gravitational wave side. So concerning the gravitational wave signal, we have a larger bunch of models that we can use. So in order to cover the uncertainty, also in this case, we decided to choose these 3 sets of emission models. The first bunch, the first 3, are the one of David, that is not more today here, but they are not rotating Corcola supernovae. The second bunch are from the Mellmeyer paper. These are rotating Corcola supernovae, fast rotating Corcola supernovae. And the last set of gravitational wave emission that we consider are considered more extreme, because in this case, the gravitational wave emission is larger due to the combined effect of rotation and also magnetic field. So if you want, these are the ones that are producing a larger amount of gravitational energy. So we use the same approach of the neutrino size. So we simulated 10 years of data, background data, then we inject the signal inside, and then we look for the efficiency, exactly the same. And these are the results. Okay, so as you can see, the situation is pretty different for the neutrino side and for gravitational wave side. So in this case, also the Milky Way will be difficult for the gravitational wave detectors, because only for the extreme model we have 100% of efficiency. For the fast rotating emission model, we have still a large efficiency that could be 80% or 90%, while for non-rotating, so for non-rotating star, this efficiency drop dramatically below 10% until inside the Milky Way. So it's really a small efficiency. And for the Large Magellanic Cloud, the situation worse, of course. And then, yes? Yes. Okay, let me check. 3D. Okay, and so for, of course, the Andromeda situation is 0, okay, but also for the Large Magellanic Cloud, the efficiency will be to 0 for the non-rotating case and 60%, 20% for rotating case. In order to combine neutrino and gravitational waves, we have some problem to decide how to use this model, so we decided to use the non-rotating case, because the rotating case is the only one that provides an efficiency large enough to be combined with the neutrino detector. So I will show you the combined case for this situation. So, but before going to the combined, let me show you what is the possibility to improve the neutrino sector by using a new shape parameter. So let me show you what is the usual way to do that analysis in the neutrino sector. So typically, when you look for, in a blind way, for a burst of neutrino from supernovae inside the neutrino detector, then you open a window that is 20-second window, and then you count inside this window how many events you have. So the multiplicity, if you want, of this cluster that is called me. And then you compare this multiplicity with the expectation that are due to Poissonian fluctuation of your background. And then you assume that this is a signal or a background if this is compatible with Poissonian fluctuation of the background. And this is the usual way. However, in this way, you don't take into account an important information that we expect a burst-like structure in our signal, not just a fluctuation, but something that is very clustered in time in a very short time window. And then we decided to insert another parameter, not only the multiplicity, not only the number of events inside the window, but also how they are distributed inside. So the Xi parameter that is called here, that is the ratio between the multiplicity of events and the duration of the signal. So the time of the last event minus the time of the first. This is like a rate, if you want, and this take into account that you expect something like this, not something like a fluctuation of a flat background. And this is a very powerful shape parameter indeed, because when you assume a threshold in terms of false alarm rate for a pure Poissonian application, so just based on the number of events, a threshold in terms of false alarm rate of 1/100 ER, it's equivalent, exactly equivalent to a threshold in number of events, because it was just Poissonian. So for case, for example, let's see Camland detector. By assuming the background of this detector, a far threshold 1/100, it's equivalent to a threshold multiplicity 8. This means that you assume that you have a signal only for multiplicity larger than 8. And this is the green region, if you want, of the plane that is accepted by this threshold. But if you also insert the shape parameter, then you can enlarge this window of accepted event to this region of the plane where the multiplicity is smaller than 8, but the shape, so if you want, the way in which these events clusters inside, show that these events are not background, just a signal, very short in time. So you allow a parameter space that is very useful for very small statistic bursts. So let me see what this does means in terms of efficiency. Let's see the case of Camland. So we injected 10 years of background data, and then we can see that these background data are all below this threshold, as you expect. So you are not including any more background. But when you insert the signal, for example, in this case, for 60 kiloparsec away supernova inside the Camland detector, then you obtain this very different situation for the standard case and the new case. So for the standard case, you can accept only this cluster, and this means a detection efficiency of 73%. With the new procedure, by assuming also this region allowed, then this efficiency will grow to 83%. It's not a big increase, but it's an increase at the horizon of the detector. So you are more sensitive at the horizon. So this is a 10% increase at the horizon. And this is very general. You can do this in any detector of neutrino sector. And this is again for the S-News alert for the electromagnetic community. So now that we use this in the general situation, let's see what is the combined results with gravitational wave low energy neutrino. So this is the data analysis procedure that I already discussed before. So we are going to do the data analysis in the gravitational wave sector, and then this will end up by using the standard pipeline with a set of triggers in gravitational wave that are characterized by their significance in terms of false alarm rate. And then you do the same for the neutrino sector, and still you have a trigger of neutrino data with their significance. And then you combine, looking for temporal coincidence within 10 seconds. Of course, you have also background in all the detectors. So this is the results for the still Camland and still a supernova 60 kiloparsec away in order to allow a comparison. And this is the case of, if you want, the neutrino model based on data and the Dimmel-Meyer model of fast rotating gravitational wave. This is the combined results. So you can see that also in this case, the detection efficiency, let's start with the gravitational wave only. So the gravitational wave only are able to recover only 33% of the signal. The other one are lost within the pipeline. So you have no any chance to recover. However, no one of these 33% signal show a detection efficiency of 5 sigma, sorry, a statistical significance of 5 sigma. So the efficiency of 5 sigma is 0. When you add the Kamland neutrino detector and you look for temporal coincidence, of course this change. And then you have that for the standard procedure, so without any shape parameter, 71% of this 33% become detection, so 5 sigma detection. When you use also the shape parameter, 83% of these 33% become detection. So this is the take-home message number 2. By adding the Kamland detector, we can increase the 5 sigma detection efficiency of gravitational wave signal of this amount. So to be from 0, 28%. Of course, this is only one detector. Well, now we can add two detectors. So we can add not only Kamland, but also LVD together. And we do the same analysis. And this is what you can obtain in the end. So in the end, you can obtain that of the 33% signal that are recovered in the gravitational wave pipeline, 100% of this become 5 sigma detection. So you reach the saturation. All the signals that are recovered inside the gravitational wave detector are really detection, so 5 sigma detection. So you can increase the detection efficiency with 2 neutrino detector from 0 to 33%. And let me stress, this is the maximum. You cannot go over because the other one are lost inside the pipeline before arriving this. Okay, so this is the summary of this combined analysis. So we quantify the supernova, corolla supernova analysis efficiency with a global network of low energy neutrino and gravitational wave detector. We show that it's possible to improve the low energy neutrino data analysis by using the shape parameter of 10% at the horizon of the detector. And this makes this method very sensitive to low statistic signal, so far away supernovae or weak supernovae. It's very fast and it's adaptive, so you can, it's completely based on data. And it could be very useful also to expand the detection horizon for future detector like Hyper-K to Andromeda. And this I will show you the results. This is the Hyper-K case, Andromeda, so a distance of 700 kiloparsec. So this is the detection efficiency that you can obtain with standard procedure, so 70% of the signal. When you add also the shape parameter, this detection efficiency increases to 85%. So this is the case of the future detector. Of course, this is only a simulation, but we have to see the real background, where it will be. Okay, now I think that I have still time. If I have still time, I will just switch a bit to another topic because I want to share with you this, idea. It's the situation of the Gran Sasso Laboratory. So I am from the Gran Sasso Laboratory. Here we have a supernova dedicated detector that is LVD, the one that I used in analysis, so 1 kiloton liquid scintillator, that's still in data taking. However, we have several detectors that are mainly dedicated to other topic physics, like dark matter direct detection or zero-less double beta decay. But several of these detectors are characterized by a veto region around that is a water tank. So this water tank is sensitive to inverse beta decay neutrino from supernovae, and then you can combine this water tank together as a bigger modular detector that can be sensitive to supernova neutrino with a very high duty cycle because it's a modular detector and very fast coincidence in time. So this idea bring to an agreement that is ongoing between experiment, but let me show you what could be a possibility in terms of physical interesting application of this idea with a failed supernova. So let's consider, for example, the case of a failed supernova. In this case, as you know, you expect that the neutrino luminosity will just drop when there is the black hole formation, and also the gravitational wave signal expected in this case will drop at the same time. And unfortunately, typically for this kind of events, we have also very faint electromagnetic counterpart, so it's very difficult to catch the position of these events in the sky, let's see the capability of the LNEGS infrastructure to identify the time of the black hole formation for a gravitational wave detector as much as possible with a very small uncertainty. So this time of the black hole formation will be related to the time of the black hole formation in the neutrino light curve by the time of flight, of course, between the detector. If you don't know the position of the supernova in the sky, the uncertainty in this term is equivalent to the time of the flight, so it could be very large if the detector are very far away. But we have a lucky situation in the Gran Sasso Laboratory. We are very nearby to the Virgo detector, just 1 millisecond of time of flight. And maybe we will be also very nearby to the future Einstein telescope if this will be constructed in Sardinia. So this situation will be still good also in the future. So I used two different models. So a fast black hole formation where the black hole just form very soon, and also a slow black hole formation. And let's see what is the capability to recover this time of the black hole inside the neutrino detector in the Gran Sasso Laboratory. So we see this, this is the case of a supernova 10 kiloparsec away. These are the detectors that are now on data taking in the Gran Sasso Laboratory that are characterized by a Veto region that is a water tank. This is the number of versus beta decay that you can expect from the different two models, so fast black hole formation and slow black hole formation in the second column. This is the average time of the first neutrino events that is observed in this detector with the uncertainty that is related to the statistical fluctuation with hundreds of simulations. And this is the time of the last neutrino events. Also, this is the uncertainty related to the fluctuation inside the Monte Carlo. And this quantity, it's the inverse of the C quantity that it's the shape parameter that I used in the other analysis. Because we realize that the uncertainty that you can obtain in the last events, it's equivalent to this 1 over C. This is indeed an agreement with previous literature, and this is very interesting in my opinion, because this quantity is completely data-driven. You don't need to model the signal. This is the different from the case of the bounds, of the starting time. So when you combine the detector, this uncertainty on the time of black hole in the neutrino sector will profit of the combination of the detector because the uncertainty will decrease. So let me show you, what you can obtain for the two cases that I considered. So for the fast rotating black hole formation and for the slow rotating black hole formation, these are the uncertainty that you can obtain in the different detectors. I just skipped to tell you that in the future, we already know that Legend 1000 also will be there in the Gran Sasso Laboratory with a bigger tank that is 980 tons of water, and also Darwin probably will be there with a also big tank. So you can also do a projection if you want of this expectation for the future, where there are Legend 1000 and Darwin, maybe combined with Einstein telescope, let's hope. And these are the final results. So this is the uncertainty that now at the present, so with the present detectors, we can give to the Virgo detectors. So we can give the time of the black hole formation with an uncertainty that is 4 milliseconds. That is pretty small. Just comparison, this is super K. Super K is bigger, so of course it can identify better the time of the black hole formation in the neutrino sector, but then there is time of flight. And this will completely destroy the sensitivity of super K in this term. So the final uncertainty will be 28 milliseconds. So this is just an idea, and maybe someone of you can use this to do something great in the gravitational wave side in order to do some matched filter that want to use this information in a very dedicated manner inside the data analysis. Till now, there is no any data analysis dedicated to this failed supernovae, but maybe this is something that can be used in the future. So thank you. And, question.
Thank you for this interesting talk.
Grazie.
I have a question about the detection capability or possibility for the gravitational waves. When you showed this efficiency of catching the signal, when you do this, would the detection actually gain from a long duration signal from a supernova, though it's kind of stochastic or unstructured? Or, I mean, when you evaluate for such an efficiency, how long do you take the signal duration to be?
Okay, so in this case, these are the models. You can see that the duration is very small in any case.
Yeah, but this is, of course, very limited predictions based on constraint theory. I mean, at the time, first of all, the lower, the Dimmelmeier plots, they were just for rapidly rotating stars and the core-bound signal. So that's the reason why it was constrained to a short period. That's a very peculiar signal from bounds of a rapidly rotating core. The upper is, of course, a very unfavorable 9 solar mass model, which doesn't produce a large signal, but and also probably I don't see the time when it was published. It was probably also less than a second. Now, such 3 have been carried to many seconds, so the signal actually continues. Of course, the frequency shifts. The signal is composed of different contributions. There is a signal from bounds, post-shock convection, the SASI potentially, and then there is a proto-neutron star signal, which shifts to higher and higher frequencies. I don't know how that could be combined in order to help the detection possibility. That's something you might want to consider. But the more recent papers have just much, much longer signal structures. Yeah.
But still it's a modeled, right?
Pardon?
It's still unmodeled, this signal, or it's possible to model in some way? So to have some prediction that is not stochastic?
Yeah, that's the nature of the signal origin. Yeah, I mean.
So probably this will not really make a very big improvement.
Okay, that was
because this is the very big issue in this analysis.
Yeah, I know for the supernovae it's a problem. Yeah, that was my question, whether this would help, though it's so stochastic, but longer, obviously. You say probably not.
Yeah, probably not, because the majority of the signal are lost when you do the first step from raw data, the widening of the noise, because you have no any information about the shape, and then you just lose the signal inside.
Yeah, unfortunately, this source, we can't do much about it. It's as it is, Okay,
unless we just construct a very complete new data analysis pipeline that is based on some very different approach.
Yeah. Thank you.
I have a simple question. So, do you consider a gadolinium effect in supercamiocandae?
Not in this analysis, no.
Okay. So, gadolinium so can...
Anyway, the super K capability is already 100%, so this can just increase with gadolinium, of course.
Yeah, gadolinium can reduce the background level so much, so maybe to the zero level.
Sorry, I don't understand.
Gadolinium so can reduce background level so much, so maybe to the zero, almost.
Sorry, I don't catch the question. Sorry.
Okay. So
is still a super K? No.
So in supercamiocan, so
yes.
So gadolinium so can decrease the background levels.
Yes.
To the
so the frequency background that I am using is larger than the one that you obtain now. Maybe.
Yeah.
With gadolinium. I have to look for this. I don't know this.
And so you can also decrease the energy threshold level. So maybe 5.8 MeV.
Okay. Thank you.
Just a very simple comment. Juno is coming into play next year. So it's a 20 kiloton liquid scintillator detector with very, fantastic energy resolution. So maybe it's worth including in this analysis.
Yes, you're right. in this analysis, indeed, there are no future detector at all in the combined analysis, but this is something that you can, of course, do. The important point, unfortunately, we need to know the background in order to do this analysis in a safe manner, because otherwise we just don't know how much background where you insert the signal. So we have to wait probably for real background measurement in order to be very safe.
Okay, so in the part, so in the very last slide, you compare the results of, yeah.
Oh, okay.
Yeah. So you stress that the combination of Grand Sasso Virgo would do better than Super K and Virgo, but why do you compare Super K with Virgo and not with Cagra?
Okay. The time of flight between Cagra and Virgo is smaller, of course. Yeah, you are right. I can do this. It could be larger in any case, but smaller than this.
Well, I suspect no.
Yes, right.
Kagra is not yet reworking, no? Kagra is not yet working. Yeah,
the
because
future.
of the earthquake. So Kajita told us that there was an earthquake. Yeah. It's a prospect, in prospective way. Other comments or questions? Okay, if not, let us thank Jude again.